Computers really do feel like magic, don't they? I mean, you've got this box of metal and plastic, you plug it into the wall, and suddenly you can watch a cat play a tiny piano from halfway across the world. But what is actually going on inside that box? So, what we're going to do is pull back the curtain and take a quick tour of the incredible world of computer science. Okay, so here's our roadmap. We're going on a journey up what's called the ladder of abstraction. We're literally going to start with sand. Yeah, this stuff on the beach, and see how that gets turned into the code that solves huge, complex problems. It all starts with silicon, which is made from sand. And that silicon is used to create billions, and I mean billions, of these tiny, tiny little switches. And that tiny little switch, it's called a transistor. Just think of it like a light switch. It can either be on or it can be off. We represent on with a 1 and off with a 0. And that simple idea, that on or off, that 1 or 0, it's basically the atom of our entire digital world. Okay, so that single on or off value, we call that a bit. Now, 1 bit by itself, not very useful, right? It's just a yes or a no. But here's the thing. You start stringing millions, no, billions of them together, and that's where the magic really starts to take off. Okay, this is where it gets really clever. We can wire these transistors together into something called a logic gate. So imagine you've got a light bulb, but it takes 2 switches to turn it on. An AND gate is like that. It will only turn on the light if switch A and switch B are both flipped on. With these simple gates, our computer is taking its very first step towards making a decision. Right, so we've got these little decision makers. But so what? How do we go from a simple yes or no to an email or a video? How do we make these ones and zeros actually mean something? Well, it turns out we just group them together. If you take a group of 8 bits, that's called a byte. And with 8 little spots that can be either a 1 or a 0, you suddenly have 256 possible combinations. And just like that, we have enough to work with. We can start counting in a language computers understand, binary. Now look, binary is perfect for a computer, but for us humans, staring at endless strings of ones and zeros, yeah, it's a total nightmare. So to make life easier, we use other systems, like hexadecimal. It's just a clever way to bundle 4 bits into a single, easy-to-read character. So now we have a way to represent numbers. What's next? Well, we just agree on what those numbers mean. We use a standard called ASCII, where every single letter, number, and symbol gets its own special number. So when you hit the A key, the computer has no idea what an A is. It just sees the code 01000001 and goes, aha, I know what that is. Okay, so we've got all this data, all these instructions flying around, but something's got to be in charge, right? Something has to actually do the work. Well, meet the CPU, the central processing unit. It's the brain of the whole operation. The thing about the CPU is it's an absolute speed demon, a genius at following orders. The catch? It has a terrible memory. It can't hold on to information by itself. That's why it's always working with a partner, the RAM, or random access memory. The RAM is the short-term memory that holds all the data the CPU needs right now. And for every single tiny instruction, the CPU does this little 4-step dance, over and over. First, it'll fetch an instruction from RAM. Then it'll decode what that instruction means. Third, it will execute the command. And finally, it will store the result back in memory. Fetch, decode, execute, store. Again and again. And when I say over and over, I mean it. The speed is it's hard to even wrap your head around. A modern CPU can run through that entire 4-step cycle more than 3 billion times every single second. So we've got this super fast brain that can do billions of things a second. Great, but how do we tell it what to do? I mean, nobody's sitting there typing out billions of ones and zeros, right? That would be insane. Of course there's a better way. That's what programming languages are for. They're this amazing layer of abstraction that lets us write instructions that actually look something like English. So instead of a massive wall of binary, we can just write one simple, clean line of code. But that human-friendly code still needs to get translated back into the ones and zeros the CPU can handle. And there are basically 2 ways to do that. A compiler is like a translator who reads an entire book and then gives you the fully translated version. An interpreter is more like a live translator at the UN, translating one sentence at a time.
All right, so we can tell the computer what to do, but what about all this stuff it's working with? All that data? You can't just throw it all in a big, messy pile and expect things to run smoothly. You need to organize it. And for that, we use data structures.
Two of the most basic are arrays and linked lists. Think of an array like a row of lockers in a gym. They're all numbered and in order, so you can go straight to locker number 57, super fast. The downside? You can't easily add a new locker in the middle. A linked list is more like a scavenger hunt, where each item just tells you where to find the next one. It's more flexible, but slower if you need to find something in the middle. And we can use these basic building blocks to create other, more specialized structures. For example, a stack works exactly like a stack of pancakes. You push a new pancake on top, and when you're ready to eat, you pop one off the top. Last one in is the first one out. Simple as that. And what about for really complicated interconnected stuff? For that, we use graphs. It's just a bunch of points or nodes connected by lines or edges. It's perfect for mapping out a social network, who's friends with whom. Or, the one we all use every day, finding the shortest route in Google Maps. So let's put it all together. We have languages to write instructions, we have data structures to organize our information. When you combine those two things to solve a specific problem, well, that's called an algorithm. And don't let the word algorithm scare you. It's just a recipe. Seriously, it's a list of steps you follow to get from a starting point, your ingredients, to a finished product, your delicious cake. That's all an algorithm is. But here's a crucial thing to remember. Simple instructions can have huge consequences. This little bit of text looks like gibberish, right? But if you type it into the right login box on a vulnerable website, you're essentially telling the database, hey, just let me in, because 1 equals 1, which is always true. And just like that, the logic of the algorithm is broken and a hacker is in. So when you really step back and look at the whole picture, it's pretty incredible. This entire unbelievably complex digital world we built, from artificial intelligence to streaming movies, it all rests on that simple, tiny switch being either on or off. It's all built on ones and zeros, which kind of leaves you with just one question, doesn't it?